So let's continue our discussion on various spectroscopic techniques and how we can apply character tables and molecular orbital theory to them. We're going to continue now looking at photoelectron spectroscopy. So photoelectron spectroscopy, or PES for short, or PES, is really what we call an orbital camera. It allows you to see where the orbitals are in terms of their energy, and it's based upon the photoelectric effect. Basically, you have to hit a molecule with enough energy to force electrons to be ejected. And so what we do is we use usually ultraviolet light, sometimes X-ray light as well. If we need something higher energy, we point it at a sample of molecules. And if there's enough energy in the photons, that energy will be absorbed by electrons from certain molecular orbitals. And if they absorb enough energy, they will be ejected completely from the molecule. And we can collect them and measure them and see what energy they must have been before they left. And so what we can look at is the overall energy. So H nu, so that's total energy that was sent into the system, must be equal to the ionization energy plus the kinetic energy of the electron. And so again, we know H nu because that's the light that we put into the molecule. We can measure the kinetic energy of the ejected electron, and so whatever's left must be the ionization energy for the orbital that the electron came out of. And that ionization energy is essentially the energy for an orbital. And so what we see in a PES spectrum is each peak that shows up corresponds to the energy of a very specific molecular orbital. And they all have their own energies, and so they eject their electrons at certain energies. So if we track them down, they're going to go from the highest energy, so the least stable electron, down to the most stable. So the first electron that comes out will come out of the HOMO, the highest occupied molecular orbital, because that requires the least energy to remove. As you start removing electrons, it requires more and more energy to remove those electrons, and so you have to add a little bit more energy. Eventually, you'll get to a point where the type of light that you're shining into that molecule can no longer remove any more electrons, and you're not going to get any more peaks. So let's look at the spectra. If we have, we'll see the pictures here in just a little bit. If we have electrons from lone pairs, so if it's a molecule that has lone pairs on it, those tend to generate very sharp peaks in the photoelectron spectrum. And this is primarily because removing electron from something that's non-bonding, a lone pair, then we're not changing any bond length in there. So we don't get any change in molecular vibration. We don't get any change in bond length. So molecule doesn't vibrate from where it was to where it's going, and it creates a much cleaner spectrum. If you start removing electrons from bonding orbitals, you start getting very broad peaks, and sometimes you'll even see some jagged side peaks on them caused by the bonds vibrating at energies very close to where it was that you removed that electron. So again, yeah, small subpeaks. So let's take a look at water. Our molecular orbital diagram predicts 4 peaks for the 4 occupied molecular orbitals. We have the 2A1, the 1B2, the 2A1, 3A1, and the 1B1. Now, if we use ultraviolet photoelectron spectroscopy, we're only going to see 3 peaks in that spectrum, and this is because of the energy of that 2A1. It's too far down, so the energy of the 2A1 is too low, it's too stable, and the requirement is too high for ultraviolet light to eject any electrons from the 2A1. If, however, we use X-ray photoelectron spectroscopy, X-ray photons have much higher energy than ultraviolet photons, and so we can actually reach the energy needed to eject that 2A1. So if we look at this photoelectron spectrum of water here, we have a few different peaks here. So we have experimental, we have calculation, full calculation. I'm not sure what SA calculation is here. but we have a very sharp peak right here, and that corresponds to the lone pair and on the 1B1. And then as we go down to the 3A1, we have this here. Now the 3A1 is frequently called the second lone pair on water. It is actually still very weakly, it's weakly bonding, but the bonding contribution is very low. So essentially they call this the second lone pair on water, but it does have a slight bonding characteristic. So it is shifted to slightly higher energy. We go to the 1B2 here next, and we see that we do have, it's between one of the p orbitals on the oxygen and the two s orbitals here. We actually drew this diagram on the salks using our salks, but here we go into a little bit different energy. And then we go through a big empty area here before we get to the energy of that 2A1, which is a very strongly bonding orbital, and so it requires a lot of energy. Again, you can see this plateau in here where the energy just has to keep increasing and increasing until you get to this point to eject that 2A1. And we see also how jagged these peaks are here, and you see there's just a series of little side peaks off of the main peak. And this becomes again from those bonds vibrating as after the electron is moved, because you've changed the bond order by removing one of the electrons.